So let's look at this mathematically. So a couple of things we notice is that the number of boxes on this side is equivalent to the number of boxes here, because 6 plus minus 3 equals 3, and we have 3 boxes here. So what we can say is that the mass and velocity quantities are conserved both before and after. We have the same number of boxes. So in other words, we can say momentum is conserved. And remember, for momentum, we're using the letter P. So initial momentum equals final momentum. And just to remind yourself, for this initial momentum, it's actually based on the red car and the blue car. And the final momentum as well is based on the red car and the blue car, as we've seen over here in our diagram. So essentially what we're going to do is we're going to now break that down even further. So in other words, I can say the momentum of the red car plus the momentum of the blue car in general is equal after to the momentum of the red car and the momentum of the blue car. So we're going to put the before as I for initial and F for final. So it's a lot of descriptive letters, P standing for momentum. Now, one of the things that we mentioned in class is that momentum equals mass times velocity. And because of that, I can replace every P with mv because they are equal to each other. So that means that the mass of the red car times the velocity of the red car in the beginning plus the mass of the blue car times the velocity of the blue car in the beginning, and we'll use initial, has to equal the mass of the red car, velocity of the red car, final, plus the mass of the blue car and velocity of the blue car, final. Looks overwhelming, but it actually will make a lot of sense once you compare your chart here to what we're going to say. So in other words, we're saying that in this case, mass, which is 2 kilograms, and we saw that because it's 2 boxes wide, times its velocity, 1, 2, 3 meters per second, is its momentum. And essentially, we're just calculating the area of these boxes. So 2 kg times 3 ms is what is going to be the momentum of our red car. So what would the momentum of our blue car be? Well, we know we have 3 boxes. The mass is 1 kilogram across, so I write 1 kilogram. And the velocity is 1, 2, 3 meters per second. And I don't even need to look at the chart. Essentially, I can look at what numbers I have here, is equal to, and we didn't actually know the answer to how fast it was going. We knew that it still had the same mass. So before we actually did the simulation or worked through it with the bar charts, we knew that the mass of the red car was still going to be 2 kilograms, okay? Nothing changed on that. We just didn't know what our velocity was. Our velocity was our unknown for the red car. And, excuse me, that should be a plus. And we knew that the mass of the blue one was 1 kilogram because it told us, but we didn't, before we did this experiment, actually know what it was. So we're just going to put a V for velocity. So now let's crunch the numbers. So it looks like this is 6 kilograms times meters per second, because I just took 2 times 3 to equal 6, plus 1 kilograms times 3 meters per second is 3 kilograms per meter per second, equals 2 kg V plus 1 kg V. Now because these two We'll do this in parentheses to make it easier. So because they have the same units, we can actually add those together again to rewrite this to be 2 kg times. So we're just rewriting it to be 3 kgV, right? Because 1 kilogram plus 2 kilograms have the same units, we can add them together. So now how do I get V by itself? And essentially what I'm going to do is, first of all, simplify. So I know I can add these two together, and my apologies, notice that I made a mistake here. It should be a negative number, okay? So please note that. So in this case, 6 kilograms per meters per second plus -3 is 3 kilograms per meter per second. And then we'll write 3 kilograms and our unknown being V. How do I get V by itself? Well, I divide 3 kilograms on one side and 3 kilograms on the other side. The 3's cancel out, the kilograms cancel out. That V equals 1 meters per second. And remember, you keep that meters per second and there's always a 1 in there. So our velocity is 1 meter per second. Is that what we actually came up with? The answer is yes. So there are multiple ways of doing this. You can solve the problem using the bar chart, but you can also solve the problem mathematically, and you'll be expected to be able to do both. So when you are writing the equation part for your work, I expect this sort of setup. And essentially, you can start right over here if you'd like to, and then plug in the rest of the numbers and solve for it. All right?